What specific problem does the warm-up stable decay (WSD) learning rate scheduler aim to solve in the context of training large language models? And how do the identified drawbacks of the cosine learning rate scheduler motivate this new approach?
The warm-up stable decay (WSD) learning rate scheduler aims to address two main issues associated with the cosine learning rate scheduler when training large language models (LLMs). The requirement for predefined training step counts and the resulting suboptimal intermediate training checkpoints. The cosine scheduler's reliance on predetermined steps complicates continual training and can lead to inefficiencies, as the model may not perform optimally at intermediate checkpoints. In contrast, the WSD scheduler eliminates the need to specify the number of training steps in advance, allowing for flexibility in training duration and enabling the model to resume from stable checkpoints. Additionally, the WSD scheduler facilitates the incorporation of high-quality data during the decay phase, enhancing the training process. Thus, the identified drawbacks of the cosine scheduler motivate the development of the WSD approach to improve training efficiency and model performance.
How does the proposed Power-LR algorithm work? Illustrate the methodology step by step, including the mechanism of learning rate calculation based on batch size and number of tokens during training.
The proposed Power-LR algorithm operates through a systematic methodology that involves several key steps. First, it calculates the learning rate based on the current number of tokens trained using a power law relationship defined by the equation eta equals a CDOT, left, frac n text tokens right caret b, where n is the number of tokens already trained, a is the amplitude of the learning rate, and b is a power law exponent. This allows the learning rate to adapt dynamically as training progresses, without needing to specify the total number of training tokens in advance. Second, the algorithm incorporates a warm-up phase where the learning rate is gradually increased to a maximum value, followed by a decay phase where the learning rate is reduced according to the power law relationship. The maximum learning rate, eta_text max, is set to a sufficiently high value, 0.02 in this case, to ensure effective training. Finally, the Power-LR scheduler is designed to be agnostic to batch size and token count, allowing for direct transfer of optimal learning rates across different model sizes and training configurations. This flexibility enables efficient training and continual learning without sacrificing convergence, as demonstrated in the experiments conducted with various model architectures.
Can you provide a simple yet detailed example to demonstrate how the Power-LR algorithm adjusts the learning rate over multiple training steps and the rationale behind these adjustments?
The Power-LR algorithm adjusts the learning rate dynamically based on the number of tokens already trained, utilizing a power law decay function. For instance, if the batch size is set to 512 and the training progresses to 1 billion tokens, the learning rate will be calculated using the formula that incorporates parameters a and b, where a is the amplitude and b is the power law exponent. As training continues, the learning rate decreases according to the power law relationship, allowing for a more gradual reduction that helps maintain exploration during the initial training phases while ensuring convergence as training progresses. This adjustment is crucial because it allows the model to adapt to varying training conditions without needing to specify the total number of training tokens in advance, thus facilitating continual learning and early stopping based on model performance. The rationale behind this approach is to optimize training efficiency and effectiveness, particularly for large-scale models, by ensuring that the learning rate is responsive to the actual training dynamics rather than fixed parameters.
What are the key theoretical or practical benefits of using the Power-LR scheduler over existing learning rate scheduling techniques like WSD and cosine scheduling, particularly in terms of flexibility and ease of hyperparameter tuning?
The Power-LR scheduler offers significant theoretical and practical advantages over existing techniques like WSD and cosine scheduling. Firstly, it does not require pre-specifying the number of training steps or total training tokens, allowing for greater flexibility in training runs as the learning rate adapts based on the current number of tokens trained. This feature facilitates early stopping and continual pre-training without compromising convergence. Additionally, the Power LR scheduler introduces three hyperparameters, eta_max, A and B, which can be tuned independently, enhancing the ease of hyperparameter optimization across different model sizes and batch sizes. The empirical findings indicate that the optimal values for A and B remain stable across various training scenarios, simplifying the tuning process. Overall, the Power LR scheduler's design promotes efficient training and adaptability, making it a robust alternative to traditional scheduling methods.
How did the authors validate or test the effectiveness of the Power LR scheduler? Discuss the experimental design, datasets used, benchmarks, and metrics that were employed to demonstrate its performance compared to other schedulers.
The authors validated the effectiveness of the Power LR scheduler through a series of controlled and realistic experiments. In the controlled experiment, they trained 1B parameter dense and mixture of experts, MO, transformer models using the Power LR, WSD, and cosine schedulers, employing a dataset of 1 trillion tokens and evaluating performance on various language model tasks and multiple-choice tasks from the LM evaluation harness. For the realistic experiment, they pre-trained two 3B language models, Power LM3B and POWERMOE3B, using a two-stage training schema with a mix of large-scale, medium-quality datasets, and evaluated their performance against strong open-source models. The metrics used to demonstrate performance included test perplexity and multi-choice task accuracy, showing that the Power LR scheduler provided consistently better or comparable performance across both experimental setups. The results indicated that even with fewer training tokens, the Power LR scheduler achieved performance on par with state-of-the-art models, validating its effectiveness.
What specific results were achieved with the Power LR scheduler in terms of model training and performance benchmarks in comparison to existing methods? And how do these results underscore the significance of the proposed approach?
The Power LR scheduler demonstrated superior or comparable performance in model training across various benchmarks when compared to existing methods like the WSD and cosine schedulers. In controlled experiments with 1B parameter models, the Power scheduler consistently outperformed or matched the performance of models trained with WSD and cosine schedulers on language modeling and multiple-choice tasks. In a more realistic setting, the Power LM3B and POWERMOE3B models, pre-trained using the Power scheduler, achieved competitive results against state-of-the-art models despite being trained on fewer tokens. Specifically, Power LM3B performed comparably to larger models, 2B to 4B parameters, while POWERMOE3B, with only 800M active parameters, matched the performance of larger dense models, 1B to 2B. These results underscore the significance of the Power LR scheduler by demonstrating its ability to optimize training efficiency and model performance without the need for extensive hyperparameter tuning across different model sizes and training conditions.